How is rocket lift capacity determined? Imagine trying to lift a heavy box with a balloon. The bigger the box, the more air you need to lift it. Rockets work the same way but with fuel and engines. They need to generate enough force to overcome Earth's gravity and atmospheric drag. The main idea behind figuring out how much a rocket can carry is called the rocket equation. It connects the rocket's total mass, how much speed it needs to reach, and how efficient its engines are. The faster a rocket needs to go, the more fuel it must carry, which adds weight and makes the calculation more complex. To find out how much a rocket can lift, engineers look at the total launch mass. This includes the rocket's structure, engines, fuel, and the payload, which could be satellites or even humans. Heavier rockets need more thrust to lift off. They also consider the propellant mass fraction, which is how much of the total mass is fuel. A higher fuel ratio means more fuel, but it also makes the rocket heavier. The efficiency of the engines, called specific impulse, tells us how well the rocket uses its fuel. Engines with higher specific impulse produce more thrust for less fuel, helping lift heavier loads. Another key factor is the delta V, which is the total change in velocity needed to reach the desired orbit. Different orbits requiring different amounts of delta V. For example, reaching a low Earth orbit needs less delta V than a geostationary orbit. The rocket's dry mass, or the weight of the rocket without fuel or payload, also impacts capacity. Engineers try to reduce this weight to carry more payload. Most rockets use multiple stages, each with its own engines and fuel. When a stage uses up its fuel, it drops away, making the remaining rocket lighter. This process allows the upper stages to accelerate the payload more efficiently. To determine lift capacity, engineers calculate the delta V needed, then use the rocket equation to figure out how much fuel each stage needs. They also consider the dry mass of each stage and the payload. By adjusting the size and number of stages, they can maximize payload while keeping the rocket manageable. For example, a single stage-to-orbit rocket must carry over 80% of its initial weight as fuel just to reach low Earth orbit. That leaves a small part for the payload. Multi-stage rockets shed empty fuel tanks and engines, so more of the initial mass can be dedicated to the payload. This way, rockets can carry larger satellites or more cargo into space. In real-world applications, engineers use these calculations to design rockets that fit specific missions. Whether launching a satellite, cargo, or crew, they balance size, engine power, and fuel to get the job done. In the end, lift capacity depends on how well the rocket's mass, engine efficiency, and mission requirements work together, all analyzed through the rocket equation and propellant ratios. This process helps create reliable launch systems for all kinds of space missions.